So great. So with that, let me introduce Daniel Scharfstein. So he's a professor in the Utah Department of Population Health Sciences, and which is within the School of Medicine. And so I was very excited when he sent me an email at the start of the fall to say that he was joining our university. He's only been here since the fall. But before that, he was a professor in at Johns Hopkins University, which is one of the top universities for bioinformatics, and so he's been there for 23 years, and so it's kind of great to have another very experienced statistician here in the University of Utah. So I'm glad he's here, and I'm looking forward to what he has to say, and to hear some more about his research.
Great. Well, can you hear me? Thank you very much.
Yeah, great.
Great. Okay. So as Jeff said, I'm a biostatistician. I spent my career 23 years at Hopkins, and I'm really excited to join the university. And so I know this is a very diverse group of people working in data science. This talk is going to be pretty theoretical. I don't sort of expect everybody to kind of get all the math, but I just hope you give you a flavor for some of the research that I'm doing and some of the ideas. And please, contact me. I have my my email address here. And so please feel free to reach out to me. I'm really excited to form collaborations at the university. And so I'm just going to talk about an area of research that I've been working on for most of my career, which is semiparametric inference. And so I'm going to tell you about my toolbox and how it works. And I work in the area primarily of how to draw causal inferences from randomized and observational studies, how to deal with issues of missing data in randomized and observational studies. And that's sort of the key area that I apply the semiparametric toolbox to. And then for people who work in the space of machine learning, some of the semiparametric stuff, we want to incorporate some of the machine learning tools, but we can't just throw in any machine learning algorithm. Those algorithms for the kind of research that I do need to perform in a certain way. They have to have certain rates of convergence. And so if anybody's on the line, either as an expert themselves on that or knows people who are experts in sort of those areas, I'd love to find opportunities for collaboration. So just these are brief acknowledgements. There are lots of people from whom I've learned about semiparametrics. So I just wanted to put their names up here. Many of them faculty members at leading universities, as well as I've learned a lot from my students over the years. So let me tell you the setup here that we have. So I want you to imagine that we have observed data on n individuals. O1 is the observed data for the first person all the way up to the nth person, and that these are IID draws from some distribution P that lives in some probability model. And what I'm interested in is learning about some functional of the distribution of P. So this psi function takes in the distribution P and it outputs to me a real number. Okay, and if there are any comments in the chat, I'm happy to stop and explain. So I have some observed data. There's some distribution that's generating that data, and I want to learn about some functional of that distribution, which I call psi. And many, and I'm particularly interested in particular types of functionals. These are what we call smooth functionals, and basically a smooth functional takes the form in this first equation. And this equation is really like a functional extension of the mean value theorem. You know, in the mean value theorem in regular calculus, you know, we have f of x, we'll call it x tilde, you know, equals f of x plus, you know, the derivative of f prime of x minus x tilde minus x plus a remainder term, right? So we all know that from sort of basic calculus. Well, there's a functional version of that where now you know, here the x is a real number, right? But here now I'm extending that, and now the x is now a distribution, p tilde. And so many functionals that we work with in causal inference or missing data or in statistics, they have this smooth representation, which is just an extension of the mean value theorem. And there are two key aspects of this extension of it's called the von Mises expansion, or von Mises theorem, is that this guy here, right, in there, which is like the derivative, it's called a gradient, and it's got two properties. One is that it has mean zero. So it's when you put in the random observation here, it has mean zero, and we assume it has a finite variance. And then there's this remainder term, which is second order, right? So in a Taylor series expansion, right, you'd have like x tilde minus x squared, right? So in distributional world, this is a remainder term, which is second order, which means it involves products of differences between p tilde and p, and that it also converges to zero when p tilde converges to p. So again, this is lots of math, very theoretical, but the point is I'm interested in learning about some functional of the distribution of the observed data, and I'm going to work with functionals that have this nice mean value theorem or von Mises expansion. Jeff, do you have a question?
So yeah, so just to put this, so maybe you can ask a question maybe to try and put this into terms I'm slightly more familiar with. So I've dealt with some distribution, say, of over text. You look at the fraction of times a certain word appears, right? You get very high dimensional you can think of it as a high dimensional distribution point, and I can think of it as a Euclidean point, perhaps, right? Depending on how I measure a difference. And then this is just standard, so just multivariate sort of derivative, but I might have a curved manifold space, right? Is that the right way to think about that? You have this remainder because you're not in Euclidean space in the representation of the distribution?
Yeah, I mean, I'm in some function space. Yeah, so it's, right, I'm in space of distributions.
Yeah, so there's some space of distributions you can actually represent exactly as a sort of vector.
Right.
Right. These discrete distributions.
Yeah, but I'm talking about, this is very general, right? So this is more general than just discrete distributions, right?
Yeah.
So I'm in an infinite dimensional space.
Sure. Okay.
Yeah.
Yeah. So like a reproducing kernel Hilbert space, for instance.
I guess so. Yeah.
But that one effectively looks like it's Euclidean, so you don't have to worry about this remainder term, right? The thing that seems different is maybe this remainder. Well,
I think there's still a remainder term. I mean, even in maximum likelihood, right? There's always a remainder term that is going to go to zero, right? Even if you're doing discrete stuff. So.
Right. Okay. So it's going to zero as the distributions get closer to each other.
Exactly right.
Okay.
Yeah.
Great.
So there's always this, right? And everything we do in statistics, I mean, in statistics, in biostatistics, we're always doing first order stuff. Anyway, so I hope that helps. Just again, I'm not expecting everyone to get I'm just trying to give you the flavor of this stuff, okay? And so this G thing, right, is like a derivative. We call it a gradient, and it measures at any given data distribution P tilde, the change in the functional from a slight perturbation of P tilde. So it's an extension of a derivative. And that equation I said is called the von Mises expansion. Okay, so now imagine, okay, I now estimate P from my observed data. Okay, so everywhere in this formula where I have a P tilde, I'm going to plug in P hat, which is an estimate of my distribution of the observed data. I have NIID draws, but I'm going to estimate this, right? And I can estimate this using fancy machine learning techniques, right? So I'm going to put in P hat, okay? So wherever I had a P tilde before, I'm going to put in a P hat, okay? And so what you get is, this is called the plugin, because I'm plugging in P hat into that functional thing. I subtract out the truth, right? Is equal to this thing where I have this guy here. This guy's called the bias, all right? And then this is the remainder term. So all I did from the previous formula was plugged in wherever I had a P tilde, I put in a P hat, okay?
So there's a question on the chat. What domain are you taking the integral over?
Oh, so this is I'm taking the integral over respect to the distribution of the observed data. So you see this little o, right? That's the argument in this integration. Okay, and then I'm integrating with respect to the distribution of little o. Does that help? Okay. So I always get confused. I have my screen and I'm like pointing at my screen. Okay, so this is bias, right? And this bias depends upon the true distribution of the observed data, right? So one way I can do is I can estimate the bias by replacing the distribution of the observed data by its empirical distribution. So this P, and I've indexed it by N, it's just like the empirical distribution. So it puts mass 1 over N at each observed data point, and I can put that bias, right? And then what I can do is when I do that, I estimate the bias, and then what I'll do is I'll move my estimated bias onto the other side of the equation, right? And then what I get is what's called a corrected plugin estimator. So basically I take my plugin, I add my estimate of the bias, and that becomes my what's called the corrected plugin one-step estimator, okay? So it removes the bias. All right, now I want to know something about the large sample distribution of my estimator. So I want to be able to learn about the large sample distribution of my my estimator. Question, Jeff?
So he's removing the bias induced by using the estimator, there's bias coming from multiple potential sources here, right? There's the actual data you have, there's the estimator that you build from the data. So this is supposedly removing the bias from the estimation process, but not from the data representing the true underlying distribution.
Correct. I'm assuming that I have some true probability model, right? So I'm not worried about model misspecification here, right? This is just the bias that's resulting from this estimation procedure. This plugin estimator has some bias in it, and I want to remove that bias. Okay, and so I remove that bias by doing what's called this corrected plugin thing. Okay, now the issue here is that to learn about the large sample properties of this, you can use like some empirical process theory, and you can like do like some fancy schmancy Donsker stuff. And I wasn't trained as a mathematician, so that stuff is kind of like hard to me. But I've learned about a technique called split sampling, which allows me to kind of understand how to learn about the asymptotic distribution of this estimator. Okay, I'm gonna use a slightly different estimator for which I can be able to understand the asymptotic properties. Okay, So how does split sampling work is I take my data set and I split it into k equally sized bits. Okay, so I could do, I can split, let's call it k10. I split it into 10 bits. Okay, and I define SI to be, and I just randomly split it, and SI is going to be the where the ith observation lives. Does it live in the first split, the second split, or the kth split? And then what I'm going to do is I'm going to estimate my distribution based upon all the data except for the kth split. So I'll use 9/10 of the data to estimate the distribution of the observed data. Okay, so if I'm doing some kind of machine learning thing, blah, 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 I'm going to use 9/10 of the data to estimate it. Okay, and then I'm going to define this guy to be the empirical distribution of my observed data in the kth split. Okay, and then I'm going to define my plug-in my one-step corrected plug-in estimator based upon the kth split to be the plug-in estimator, where I just use the data from everything except the kth split, and I'm going to use my bias. My estimated bias stuff is going to be, well, over here I'm going to put in my distribution, everything except the kth split. And here I'm going to use the empirical distribution of the observed data in the kth split. And what this does is it separates this from this. So this is built on 9/10 of the data, and this is built on 1/10 of the data, right? And now they're independent of each other, right? And that makes the asymptotic theory that one wants to do, it makes it like super nice, okay? So I'll get 10 of these numbers, okay? And then I'm gonna average them to come up with my overall estimator, and that's gonna be my split sample estimator of my parameter of interest, okay? And now what you can do is you can write an expression for this split sampling estimator minus truth can be written as an expansion of 3 terms, okay? So let's not worry. So there's going to be a remainder term that looks like this and a remainder term that looks like this. We don't have to focus on the actual details. Okay, and then we have this guy, all right? And now what can be shown, what has been shown in the literature, okay, is that, so what I want to do is to show that these terms, what I ultimately would like to have is that these terms converge to 0 at certain rates. And so that I have like my classic, if you ever learned about maximum likelihood and stuff and do your first order thing, you kind of have like a IID sum of random variable, like the central limit theorem. You have an IID sum of random variables plus a term that goes to 0, right? That's what we ultimately want. And so we're going to want these remainder terms to go to 0. And this whole bit over here is going to behave like an IID sum of random variables, which we can use like a standard central limit theorem on, right? So we're going to have like, we can express this as an IID sum of random variables plus 2 remainder terms, which we want to go to 0, okay? So basically, in order for these remainder terms to go to 0, we have to show 2 things. So one is the norm of my gradient evaluated at my estimator built on 9/10 of the data minus the gradient at the truth. That's got to converge to 0. And my estimator on 9/10 of the data has to be sufficiently well behaved. And if it is, and I'll talk about that in a second, and the fact that my remainder term is second order, that it's a product of things, we'll make sure that the second remainder term goes to 0 at the right rates. Okay, so ultimately what happens is, I was trying to say, is if I blow this up by root n, which is the classic statisticians love root n because we like central limit theorems, we get an IID sum of random variables plus a remainder term, which is going to converge to 0, okay, under certain conditions.
So can I ask a question?
Yeah.
So I'm curious why you're working and focusing on the gradient of the distribution as opposed to just the convergence of the distribution itself, right? As you get better estimates of the data, you get an estimator of like the underlying function you're trying to understand, you're getting a better estimate of that. What's the
Okay, so you're saying just focus on, like, just choose some estimator of the distribution that basically gets closer to the truth as n gets large.
Right.
Right. But in statistics, we want to be able to draw inferences in finite data with reasonable amount of precision. So we want our standard errors to be, reasonably, like we might have an estimate, but our standard error is huge, right? Or get a confidence interval, it might not learn anything, right? So we can't just like use any distribution of the observed data and be able to get precise enough inferences. So I work with clinical trials and observational sites. We have thousands of patients. I know that when you work in big data, you've got millions and millions of stuff, right? I work on the orders of thousands. So we want our estimates of the thing we care about, these causal effects, right? We want them to be reasonably precise. Okay. And so I just can't use any just distribution, as you'll see, hopefully soon, in order for the thing I care about to be, to have reasonable precision. That is to behave like root, to have standard errors on the order of root n.
Yeah, so is the fact that the gradient is well defined and you can bound it, that's restricting the class of the distributions, or is that also because a causal inference requires kind of a difference between two distributions, and that's what the gradient is captured, so that's why it's important to approximate. Because I mean, if you can restrict the class of distributions in other ways, it could be a kernel density estimator, and then you can use all this kind of this kernel approximation theory.
So again, I think you're focusing on the level of the distribution of the observed data, right? About estimating that distribution, rather than the target parameter that I'm interested in, which is some smooth functional of that, and it's that target parameter that I want to draw inference about. Okay. And I need that gradient to help me with that. Okay. I don't feel like we're answering your question well. It's a good question, but it is because I'm focusing on the target parameter of interest, not the distribution of, I don't really care about the distribution. It's a nuisance to me, but what I care about is the target parameter. And so the gradient comes into play from the semiparametric theory.
Great.
Okay.
That makes sense.
All right. So there are many choices for the gradient, but there's a theory that was developed many years ago, and there's one that's optimal. There's an efficient gradient, and that's called the efficient influence function. And if you use that efficient influence function, I will get the most efficient. I will compute an estimator which has the smallest variance among all other, among competing estimators that are all converge at root n rates. So there's a theory about how to compute the best gradient, and it's called the efficient influence function. Okay. Now, how do I find the gradient? Again, I'm not expecting to get all the details, but why is my screen not moving? Is my screen moving?
I can see your cursor, but okay, it's good. Moved. Okay,
fine. Okay. So basically, the gradient is a solution to an integral equation. And it has this form. Again, I don't know you did the details, but basically what you do is, so there's something called a tangent space, which is like the space of all scores. So you think about maximum likelihood, there are score functions. Now we're in infinite dimension, like we're not in parametric models. So there's an extension of tangent spaces. Basically, it's the union. So if you're in a semi-parametric model, there's you can define a set of little parametric submodels, and in each parametric submodel you can think you have scores, And now if you take the union of all these parametric submodels, you create something called a tangent space, okay? And basically, if I take an element from that tangent space, so this is just an element from that, like a score from that tangent space. If I take the derivative of my functional of interest in some parametric submodel, it has to solve this integral equation. I don't think I'm going to be able to explain all the details of it, but just suffice it to say that the gradient has to have certain properties, okay? All right, and so in semi-parametric world, I you know, and there's, you know, a bunch of people who work in this space, we know how to do this, okay? There are all these techniques, and it involves projections and functional analysis. There are ways of sort of getting at these gradients, and there's ways of getting at the efficient influence function. Okay, so now I'm going to move to an example of implementing this theory, okay? And I'm going to implement it to learn about causal effects in something called, what's called a comprehensive cohort study. So I'm switching now from the sort of uber theory of semiparametrics to now an example, and I'll illustrate some of the concepts. Okay, so imagine now I'm interested in comparing two competing treatments, A and B. All right, and what I do, so I approach it, so I have a population of patients, I grab a sample of them, and I go to these patients and I say, hey, would you like to be in a randomized trial? And if they say yes, I flip the coin, fair coin, and I assign them to treatment A or treatment B. If they say no, I say, hey, listen, I know you don't want to be in the randomized trial. How about you join an observational study? You can choose your own treatment. You can choose treatment A or B in discussions with your physician, but we won't flip the coin, okay? And I just want to collect the same kind of data as I would in the RCT, okay? And so this is called a comprehensive cohort study. So we have both an RCT component and a observational component. All right, so here's some notation for the data that I would have in this, this comprehensive cohort. So I have a bunch of baseline covariates, that is covariates measured before the treatment decision is made, all right? I have an observed outcome, Y, that I want to measure on each patient. So if it's binary, I might say, did people survive 90 days? 0, 1 indicator after treatment, right? Or it might be some continuous measure, you know, of their function. Then I have something called a randomization indicator. So whether or not you signed up for the RCT. So it takes on the value 1 if you decided to go into the RCT, and it's 0 if you decided to go into the observational arm of the study. And then T is the indicator, did you take treatment A or did you take treatment B? Okay. And the observed data for each individual, now that's my O. Remember I said I started out with saying I have IID draws. So my observed data for each individual is going to be their vector of baseline covariates, their outcome, whether or not they signed up for the RCT or the observational study, and then their treatment indicator, whether they got A or B. And I assume that I have NIID draws from some distribution P that lives in some probability model, space of distributions. And I will use the subscript I when I'm talking about the ith patient. Okay, so that's my up now. So now I have IID draws. Okay, yeah, go ahead.
You assume the IID influences their choice to be in the randomized trial or not?
The what? Sorry.
So do you assume this distribution, it influences their choice? Certain types of people are going to choose the randomized trial.
Oh, yeah. So I'm going to account for the. I'm ultimately going to account. I'm going to make some assumptions in order to be able to, and we'll see. Yeah. Okay. So in causal inference, we sometimes we often, so one theory of causal inference defines what we call potential outcomes or counterfactuals. So there's a whole theory of causal inference based upon potential outcomes and counterfactuals. So what I'm going to do is imagine for each individual, right, the following quantity. So I'm going to imagine for each individual what their outcome would be had they, so one means treatment A. So had they taken treatment A and enrolled in study little r. And this one says, what's the outcome had the person taken treatment B and signed up for study little r, right? So I really have 4 of these: Y11, Y10, Y01, Y00, okay? And first thing is I'm going to assume is that whether you sign up for the RCT or the observational arm, okay, if you receive treatment little t, you're going to have the same outcome. So for example, if a person takes treatment A, but received it in the context of an RCT, versus if the same person received treatment A, but in the context of the observational arm, they're going to have the same outcome. If they're going to die, if they took treatment A, then and they're going to die in the RCT, or they're going to die in the observational arm. Okay, as long as they took the same treatment. So this is called the single version of treatment assumption. Okay, that is, they're getting the same care in the RCT versus the observational. Okay, as long as they got the same treatment. And what I want to learn about is something called the comprehensive cohort causal effect, which is this difference. Okay, so what do I mean by this? So mu1 is, what is the mean outcome had everybody in the study received treatment little t? Okay, so 1 means, what would be the mean outcome had everybody in the study received treatment A? And mu0 means, what's the mean outcome had everybody in the study received treatment B? Okay, and because I'm talking about the same sets of people, this is a causal effect. The only difference that I'm talking about is that everybody receiving A versus everybody receiving B. Okay, now I can't estimate this causal effect without making some additional assumptions. And Jeff was alluding to this. I'm going to make some assumptions in order to draw causal inferences. So these are called, what we call in their technical words, called identification assumptions. Identification means, if I had an infinite amount of data, would I be able to tell you the answer? Okay, so the first assumption I'm going to make is that within the RCT, okay, so for people who sign up for the RCT, treatment is randomized. So if treatment is randomized, I remember it's a flip of the coin. Treatment has nothing to do with the baseline covariates. It has nothing to do with your potential outcomes. They're completely, it's completely independent. So this notation means that the flip of the coin in the RCT, the flip of the coin has nothing to do with your baseline covariates, nothing to do with these potential outcomes. Okay, and that's an assumption that's satisfied by the design. Okay. In the observational arm, what I'm going to assume is, for people who sign up in the observational study, I'm going to assume that treatment is randomized, but it's randomized within levels of X. So within levels of age, gender, all the X's I measure in the randomized trial, I'm going to assume that's basically conditionally randomized. Okay, so some people call this the no unmeasured confounding assumption. That is, I've measured all the confounders, or the variables that explain why a person chooses treatment A versus treatment B. Okay, so this is called, and that could very well be violated. It's a very like if you see people who do propensity scores or do inverse probability of treatment weighting or do any of these methods, they're making this no unmeasured confounding assumption. Okay, they assume they have all the measured variables that explain the decision to take treatment A versus treatment B. Okay, well, also, so there's something called no interference, which means basically my outcome has nothing to do with Jeff's outcome. Okay, the fact that I live or that I made a choice doesn't affect any of Jeff's outcomes. Then we make a consistency assumption. These are consistency, which basically says that if I take treatment A, then my observed outcome is equal to my potential outcome under treatment A. If I take treatment B, then my observed outcome is equal to my potential outcome under treatment treatment B. So this notation means, so if T is 1, right? If T is 1, then my observed outcome equals Y1. If T is 0, right, then my observed outcome is equal to Y0. And that just connects the potential outcomes to the observed data. Jeff, are you going to ask a question?
Yeah, so you're assuming that there's no noise here, like someone fell off a bridge and they died, so that it contributes to the death rate of the people with an effective treatment. You're assuming that doesn't happen?
Yeah, so we're not looking at the necessarily cause of death here, right? So we're just like so an example, just to live or die by 90 days. There are other methods, like if we want to know like death from a specific cause. I mean, that could be the outcome as well. But here, this assumption is nothing about, this assumption is just basically saying, I observe some data, how does it get connected to my potential outcomes?
So are these distributional quantities, or is this like deterministic? You do this treatment, you will live. You do this other treatment, you won't live. Or is there like rates that you're observing and estimating? Because it's,
so I observe for each patient whether they live or die. I observe their Y. Each patient in my data set, it's a live or die thing. And then I have got a data on thousands of people, let's say 5,000 people. So I have 5,000 numbers. Is that, I don't know if
okay. So each individual person, they effectively have a deterministic effect from the treatment for that individual.
Well, no, but I never observe. Okay, so the thing is, I never observe for any one patient what their outcome is under treatment and what their outcome under A versus B. I only observe them under one of the treatments. So I can't make any causal inferences at the individual level. I can't say for person A, for John, right, what his outcome is under treatment A and what his outcome is under treatment B. I just get to see it under the treatment he actually received.
Sure, but I mean, there's just some language I was confused about how specific it was about how they get, you said something like they get the best possible outcome, meaning that if a treatment could have cured their cancer, then it will cure their cancer. They will not die from cancer.
No, I didn't say that. I don't think I said that.
So I mean, I forget the exact word you used, but it seemed like extremely like there wasn't going to be any noise in the observations given the treatments. And I just want to clarify. So you're still observing distributions, and you're saying, okay, if
no, I'm observing data. I'm observing.
Right. Okay. So you're observing these empirical distributions.
Yeah, exactly. I'm observing for each person. Remember, coming back to here is what I observe on each person is this. So I'm not observing distributions. I'm observing data, and then I'm going to estimate distributions.
Yeah, so sorry, my lack of statistical foundations. All my distributions are empirical. So,
okay.
So you're observing these empirical distributions.
Yeah, so I have empirical distributions, correct.
But you're assuming that there was an effect caused by treatment.
I'm not assuming anything like that. I want to learn about it from the data. I'm not assuming it.
But
I want to use the data to learn about this.
The effect could be zero. It could be no effect.
Correct.
Right? But are you assuming that the outcomes are determined entirely by their, okay. So you're determining that the outcomes are entirely by the X characteristics you've gathered and the treatment effect. There's no like noise in the process. Like of the people who are exactly this age and this gender and this weight, and you apply this treatment, then they will either live or they will die, or could it be 70% will live and 70%?
Of course. So I might have people in my data set, right, who are the same age, same gender, blah, blah, blah. Some lived, some died.
Sure.
I'm not assuming it's deterministic. Sure. I mean, this is a sample. This is a sample from a population. So I have uncertainty.
Yeah.
Yeah.
But so the treatment is changing the underlying distribution, and then you're making observations on that effect. But it's has the.
Not sure what you mean. So, I mean, this is
I-
no
I-
different. This is no different than saying I observe NIID observations of X, and I want to learn about the mean of X.
Sure. Yes. Okay.
Yeah.
I think I'm introducing confusion. So
Yeah.
let me drop it.
If anyone else wants to comment, maybe help, because this is, because we're from different disciplines, so we use different language, and sometimes, yeah. So Ben, it looks like Ben might want to say something.
Well, I just wanted to say that they do have noise. I think it's like you could view that kind of holistic distribution as there's like a conditional distribution on their outcome given the treatment they have and given their covariates, but there's uncertainty in that distribution. It's not fixed that if they have these characteristics in this treatment, they will have that outcome. It's a distribution of outcomes conditional on those.
Sure.
I don't know if that's helpful.
Yeah. So that's great.
Okay. So sorry about that.
Yeah, no, it's
okay.
It's obvious, but yeah.
It's just, I think it's just different language. Okay. So we also make something called a positivity assumption, which says basically within each study arm, RCT versus observational, and within each level of covariates, there's a positive probability of receiving treatment A versus treatment B. And then there's some kind of like, finite moments stuff, blah, blah, blah. Okay. So these assumptions basically tell me that what treatment I take doesn't depend upon my potential outcomes. Okay. It doesn't depend upon on things that are unobserved. Okay. So basically I can represent my treatment mechanism, like what treatment you take depends upon what study you're in, whether you sign up for the RCT or not, and your covariates X. It doesn't depend upon these potential outcomes. That's sort of the no unmeasured confounding assumption. And furthermore, that if you sign up for the RCT, your treatment selection has nothing to do with your covariates. It's the flip of the coin. It's that 50-50 flip. So basically, if you sign up for your for the RCT, the investigator flips the coin, and it's a known probability. And if you sign up for the observational arm, then your treatment probability does depend upon your X's. People who are older may be less likely to get treatment A versus treatment B. And that means that I can write my treatment selection probability as being, so if you sign up for the RCT, then it's just a flip of a coin. This is a half, okay? And if I sign up for the observational study, then it depends upon X's, all right? So that's some notation. So this pi represents the treatment selection probability. And then I'm also going to define something called tau, which is the conditional expectation of my potential outcome under treatment T, given what study I sign up for and my X's. And because I've made these assumptions, what it means is that this regression function, right? It's identified from it depends upon the observed data, and it's actually equal to this classic regression, which basically says it's the mean of my observed outcome, given that you signed up for, that you received treatment little t, you signed up for study little r, and your covariates X. So this is just a traditional regression. Okay, so this is what this notation. So there's a pi and there's a tau. Okay, now under these assumptions, I can write a formula for my functional of interest. So remember, I started out, I said there's a psi that depends upon the distribution of the observed data. And you can write down a formula, this should really be a star here, for this is my functional of interest. And it's written in terms of the distribution of the observed data. These stars shouldn't be here. Sorry. And so this is the formula for the, there's actually two formulas I can write down for it. This is called the inverse weighted formula, and this is called the outcome regression formula. I don't know why there's stars here. Okay, I feel like I maybe, yeah, the stars on this slide should all go away. Okay, sorry about that. So that's what, so this is when I say that I wrote my functional, my parameter of interest as a functional of the distribution of the observed data, this is it. I've written it as a functional of the distribution of the observed data. Now, I can now do my von Mises expansion and figure out what my gradient is. Okay? I can figure out what the gradient is. And it turns out there's a unique gradient. There's only one that satisfies that formula. And this is what it is. Okay? I mean, I did a bunch of math behind the scenes. This is the math behind the scenes. And what this is called, so if you know any of the statistics literature, this is called an augmented inverse probability of weighted estimating equation, or augmented inverse weighted estimating function, inverse weighted. Here, this thing, you see the observed outcome is inverse weighted by this quantity. So like in survey sampling, you'll see stuff, people do inverse weighting and people do inverse weighted in causal inference, plus an augmentation term. That's the augmentation term, okay? Again, you don't need to know all this math, but that's the gradient using the technology of semiparametrics. Then this gradient has certain features though, and it has something called double robustness. If you've ever heard that term, it has a robustness feature. And basically this gradient has mean zero, even if I misspecify my models for the treatment mechanism or the outcome regression. And so I won't get into all that stuff, but basically this is if I use this technique, and I'm going to do the split sampling thing, my inferences are going to be robust, even if I misspecify certain models. Okay, so that's kind of cool. It's a double. I'm going to, in this interest of time. So this is what this says. Okay, then I need to work on my remainder terms. Okay, so you can write down, so again, using math, I can write down a formula for my remainder terms. Okay, so this is my first remainder term. Okay, and what you can show for this first remainder term is that it's bounded. You use Cauchy-Schwarz, like things that I learned in like basic real analysis, or like Cauchy-Schwarz, triangle inequality, relatively easy stuff for bounding things. And I can bound it by the sum of three terms. And as long as my estimators are consistent for the truth. So I'll have estimators for the treatment selection mechanism, and I'll have estimators for my regression functions. Okay, so these are the regression functions. As long as they are consistent, then I'm in business. Nothing about rates here. Okay. Now look at my remainder term. Okay, so remember that was R1K, whatever. There were 2 bits, and then there's this other bit which is the remainder. So this is R2K. Again, Cauchy-Schwarz inequality, triangle inequality, stuff like that. And now what you see is the remainder term is bounded by the product of 2 things. Okay. And in order for this, and so in my particular application, I'm going to use generalized additive models for estimating the treatment selection mechanism and my outcome regressions. So I'll use generalized additive model, which is like I don't know if you guys probably know about that. And we know the rates of the convergence for the generalized additive model. And so the fact that we know the rates means that my remainder term is going to go to 0 fast enough. Now, I don't have to use generalized additive model. I like to use fancy machine learning techniques. Like I'd love to use neural nets or whatever you guys know about these machine learning. I don't know about them, but you guys know these fancy machine learning things, right? The question is, and so I'd love to use cool machine learning things for my treatment selection mechanism and my outcome regression. But what I need though is that when I take the product of your machine learning guy, So if they're consistent, that's fine, right? So they're going to go to the truth, right? But I need the product of them to converge at fast enough rates in order for this guy to be convergent probability to 0. And so I need to know the rates of convergence for your machine learning algorithms. And if I don't know the rates, I can't, so that's where if I don't know the rates, then I'm screwed in terms of being able to estimate my target parameter of interest at reasonable, at the rates that we as biostatisticians like, which is root n. Yes, you can give me consistent estimators, but that doesn't necessarily mean that I can get nice size confidence intervals and small standard errors in finite samples. So what I would love, so if you have some fancy machine learning algorithm that you love, but you know the rates and those rates satisfy my conditions, I want to talk to you. If you don't, I don't want to talk to you. I'm kidding. But that's the idea. Okay, so I only have a few minutes left, and I know, so I applied this to a particular study. So there's something called the Berry study. So these are people who have heart disease and they need treatment for their heart disease. So either they undergo open heart surgery or they undergo some stenting procedure. Okay, and we have about a little under 4,000 patients who had severe angina or ischemia. Of these, so they were approached to be in the study. 1,800 agreed to go into the randomized arm study, and 2,000 agreed to go into the observational arm of the study. Okay, so that's the kind of numbers I'm talking about. I know you guys work with way bigger data than me, so I'm a small data guy. All right, we made some exclusion criteria because of some data problems. So we excluded a few patients. 996 people in the observational arm and 33 in the RCT. We used 12 baseline covariates. So that's our vector is 12. We have age, sex, education, blah, blah, blah. Some of these people were missing some of their baseline covariates. So we excluded 149 patients, and there were 4 patients who weren't followed for 5 years. Okay. So we got rid of a bunch of people just to make this a simpler analysis. And our outcome is live or die by 5 years after treatment. After treatment you started, okay? So at the end of the day, we analyzed about 3,500 patients, 1,700 in the observational arm and about 1,700 in the RCT. And in the RCT, because we flipped the coin, right, 50% got stenting, and 50% got the open heart surgery. In the observational arm, now we don't have random, you have to you self-select, right, with your physician. Here now we have 65% of people chose stenting and 35% chose open heart surgery. And now when you look at the distribution of the covariates between people who signed up for the RCT versus people who signed up for the observational arm, when you look down in the RCT, what you'll see is really good balance between the two arms with respect to these covariates, right? They've got the same age roughly, same gender distribution, blah, 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 right? But when you look at the observational arm, because people self-selected treatment, you don't have the benefits of randomization anymore. And so you can see some key differences. For example, if you look at proximal left anterior descending disease, if you look at, well, 32% of patients in the stent arm had this left anterior descending disease, but 46% had it in the open heart arm, right? If you look in the RCT, it's, they're pretty much right on the money, right? So that's one example of some, huge difference between the two arms. If you look at smokers, right? 23% were smokers for stenting versus 17% in the cabbage arm. When you look at it, if you look at it in the RCT, they're much closer, right? So that's the problem with observational arms, is that there could be factors that explain the treatment difference, has nothing to do with, the actual treatment effect, right? So now we can take the results together and we can say, okay, so we can get estimates. We can apply our technology, and what we see is that about 10 a little under 11% people died under cabbage. I don't remember which. Oh, now I'm sorry. Anyway, I don't think that's really that important right now, just in terms of this didactic illustration, and about 9%, and the difference is a little under 2%. Okay, and you can see that there was still an appreciable amount of uncertainty, and so we couldn't conclude from this analysis that there was a big treatment effect of cabbage versus stenting. We did just a simulation study. Just going to finish up here, just to show you just a particular feature of this, that if you model, so if I were to model my treatment selection process incorrectly, but I got my outcome regression correct, I still get low bias and I get good coverage of my confidence intervals. If I model my treatment selection mechanism right, but I get my outcome regression wrong, right, I still get good coverage and low bias. If I get them both wrong, then you see everything goes to hell. So this is just showing you the robustness of the procedure. You don't actually have to get both models right here in order for you to for this to work. You get this nice robustness. This is not a general thing of semiparametrics. It just happens for certain types of causal inference problems. You get this kind of robustness procedures. So I'm going to my last slide. So I try to give you a flavor. I know that you guys didn't get the math because it's hard. I wouldn't get the math if I haven't been doing this for years. If something sparks some kind of connection with you where you'd like to learn more, or where you think there might be some intersection of interest, please reach out to me. I'm particularly interested in understanding how I can make these procedures more flexible by using some cool machine learning techniques. But I do need, rates to make this work, right? So I really would like to borrow from for those who are machine learners, I would love to borrow from your toolbox to make my toolbox better. And I think I'll just stop here and take any questions or whatever. Yeah. So thank you.
So thank you. So thanks for the kind of so nice job of bringing it like a nice intuitive overview of this complex area. At least from our perspective, it definitely seems kind of there's a lot of new ideas, but I think a lot of things that look familiar, like k-fold cross-validation and gradients, are very familiar in places like machine learning.
I have a question.
Yeah, go ahead.
Who's this?
Is there any other?
Can you introduce yourself? Sorry, just so I can know who you are.
I'm Dai. I'm an undergrad at the U.
Oh, good. What's your name?
Dai.
Dai. Okay, Dai. Go ahead.
I was wondering, is there any other applications to all this like prediction other than what you discussed so far?
Oh, there's tons of applications. There's a whole literature on semiparametric theory. So used a lot, yeah, I mean, it's all over. So, I mean, there are applications to missing data. There's to causal inference. There's application to, regression. I mean, it's all over the place. Wherever you're trying to learn about some parameter of interest, but you want to be very there's a whole field of semiparametrics. There's survival analysis and.
Did it also make medical predictions and everything for doctors?
Yeah, so there's a whole theory of like optimal treatment, dynamic treatment regimes. There's a whole literature about that. Yeah, but this is not about prediction per se. Like, I'm not trying to predict an outcome. I'm trying to learn about the effectiveness of different treatments. But it could be like an optimal treatment regime that I can learn about. But it's not about prediction per se. Okay.
But then, if you're trying to predict the effectiveness of something, wouldn't that kind of predict if a patient could survive or?
So I'm not trying to predict at the individual level. I'm trying to predict at a higher level, at a population level or a subgroup level. So I'm not trying to say for John Smith, would he or she do better under treatment A versus treatment B? I'm only trying to learn about things at a higher level, at a population level or a subgroup level, or that kind of thing.
Oh, okay. So a doctor could not like use this thing on like an individual patient during a treatment or something.
Well, they could. If you think about how we approve drugs in this society here in the United States, or even in Europe or elsewhere, what do? We do a randomized trial, right? And we see that, people who took treatment A do better than people who took treatment B. I'm going to approve the drug, right? And now I'm going to treat people who have a certain, disease with treatment A because it did better, right? But I didn't learn from that RCT for John Smith, right? Those RCTs are not designed to learn for people who look exactly like John Smith whether A would do better than B. Do you know what I mean?
Okay, I see what you mean.
Yeah, I think so. What I think an interesting area is, and what I'm excited about Utah, is that we have access to very large databases. And so I'm excited to do, and I'd love if other people are interested, is to use some of these large databases to see if we can actually do some better inference about subgroups of populations, and say people of this certain type, and build dynamic regimes to say, okay, initiate on treatment A, right? And if you fail, then take treatment B or take treatment C, and maybe it's subgroups of patients we can learn about. I think it's going to be because we never observe people under multiple treatments, like, the counterfactual, what would have happened to them had they not taken, had taken the alternative treatment. I think things are going to always be kind of like at a subgroup level. But I would love to work with these large databases and to start to do some of this sort of more precision medicine.
Okay. All right. Thanks. Interesting.
Yeah. So do you think you can go back to that slide where you circled the things that you hoped machine learning would help with? Kind of as soon as you'd circled on them and you kind of moved on, and I missed whether like exactly what these are saying. So
what we need here, so this is R2K, right? So this is R2K. Let me actually erase what's here. How much time do we have? Do we have a few minutes?
So yeah, so usually we listen until 1:10 to handle questions.
If anyone needs to get off, please, feel free. So we need root n k times this term to be little op1, right? So we need to it converge to probability. So I take root n k here, right?
Right.
And I multiply by root n k, right? I need the product of this whole thing to be op1, convergent probability to 0, right? Now I can get I can get that. Like this thing doesn't necessarily. So like if this was like let's see, capital OP n to the minus a quarter, and this was capital OP n to the minus a quarter, or something like that, then this would work, right? But I could have this going at, so this first term could go at slower rates as long as this term went at faster rates. So I need the product in total to be
sure. Yeah.
Yeah.
So I'm trying to understand just kind of if you can review what these two terms are. Like I've lost track.
Okay.
Of
So this is right. So this is okay. Good. Sorry. Yeah, I know I went super. Okay.
So it's fine. I'm like almost there, but you can.
It's okay. No. So this is the probability that you take treatment T given R equals 0 and X equals X. So this is like, you can think about it so this is just like the outcome is binary, and I have 12 covariates, right? And so I would like to do some kind of like machine learning thing on, so I have a binary outcome. So I don't, and I've got a bunch of covariates. And so one thing that we do in statistics is we use like generalized additive models, which says that, okay, you with me? But I imagine you have some machine learning algorithms, right? You could do, a cart, some kind of regression tree kind of thing, classification tree to do this, right? I'm sure you can do.
Yeah.
So that's one.
So most of the kind of, so first of all, just to think of the big picture, almost all of machine learning is driven by the rates which are measured empirically, not with proofs of rates. There are some things that show proofs of rates. Now, most of those are driven by data. They're saying, make this assumption on your data, and then you can maybe say something about the rate or the accuracy about.
Right. So I'd be willing, so there's certain smoothness conditions probably, right? Or sparsity conditions or blah, 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 right?
Well, are these data sets actually distinct? How mixed are the distributions? There are ways of quantifying that.
Right. So I'm open to that, and see, I'm open to imposing some, assumptions on, I'm sure when you do the generalized additive model stuff, there are assumptions on certain smoothness stuff and other things. This thing here is the probability of dying under, again, signing up for the observational study X equals X. So this is also kind of like a binary outcome with a whole bunch of covariates that are here. So it's just like, if you're doing parametric model, this should be a logistic regression where you fit.
Sure.
Generalized additives are more flexible, but you can imagine doing, these regression, classification trees and all, those random forests, right? You can do random forests here, right? The problem is that, so if you do random forest, right, the X's, some of them are continuous, some of them are binary, some of them are categorical, right? And do we know anything about, the rates of convergence, at least under some conditions, for random forests? I don't think we do. But I know if everything was discrete, I can get rates for random forests because I've done that in another problem. But when things aren't discrete, we don't, but, I don't know, will neural nets work here? Will other, fancy schmancy stuff work here?
Yeah, so I think the thing that's most likely is these machine learning models might give you a thing that on your data possibly converges at a much faster rate. If you looked at your actual data and you slowly fed it into the model and saw how it actually converged to what it was supposed to, it quite possibly could converge at a much faster rate.
So that's not something right. So that's not something So the question is, as a frequentist, we're talking about like repeated, like if I were repeated sampling, right? So on a specific data set, that's not what I'm thinking. I'm talking about as an estimation procedure.
Yeah.
Yeah.
So then there are things that, if the data can actually be separated, then under certain models, you can get faster convergence. Or
what does it mean to be the data to be separated? You're talking about
so you're usually looking at a class of ways you can build a classifier. Like you have a linear model that in some parametric space draws a line, or it can be a polynomial model, or it can be something more complicated.
Yeah.
Right. And under that space of models, is there a line I can draw? Right. Then
so like a separating hyperplane kind of stuff.
Yeah. So then how many data points do I need to find a line that separates the actual true underlying full distributions from what with only an observation and have a small amount of error? Then that, for instance, can have a faster rate than if you knew it was not separable. Then right. So these are kind of very data dependent. You have to assume some niceties which you don't know about the data. You can't ever know where you can assume faster convergence sort of properties. So I'm personally not aware of any other way you can move past this. So Tom Alberts was in here. It looks like he's left. He may have looked at some of this stuff. But
Yeah, I could talk to Tom. Yeah, I've met him. Yeah,
yeah,
I'm glad that, yeah.
Yeah, so I'm not I'm not aware of very much at all work that I'm it's a huge enough field. There may have been
Yeah.
people who've looked
No,
at
there
it.
are people, I mean, there are people working on this. So, I recently collaborated with someone where we were able to prove some results for random forests where everything was discrete, and we were able to, to do that. And I know there are people working on this.
Yeah.
It involves like, mathematics that are probably beyond my capability. But there are people who just like this stuff, and like I've been working a lot with I've been working with single index models now, collaborating with a guy in Taiwan, and so we've been able to establish some results for, it depends, and there are these, there are bandwidth selectors, and you got to get the rates of the, it's like complicated stuff. So, but there are people who kind of love that, and so, hey Ben, you want to say something?
Sure. Just one seems like could be a fruitful place to look for these convergence rates are also neural nets. I think depending how they're set up, those are often, say if you have a continuous outcome, those are like a nonlinear least squares with like a ridge tuning parameter sort of setup. So they seem, and then even if they're categorical outputs, it's a kind of a multinomial type log likelihood with a ridge penalty again. So they seem like they could be fruitful ones to look for these nice convergence rates as well.
Yeah. Oh, cool. Great. Well, Ben, if you come across anything or want to work on it, let me know.
Yeah. If either of you, have, can speak with some kind of confidence about these sort of results, I'd be interested to hear about them. So,
right.
Yeah,
and
so,
if anybody, and I mean, this is just one area of my research, but if anyone, wants to work on some, evaluate treatments, either static or dynamic, and some of these large databases we have here at, access to at Utah, I would love to get involved with that.
Yeah.
Hey, Dan.
Yeah. Oh.
I'm sorry. Go ahead, Jeff.
Oh yeah. So I just want to add one comment on this. So I've worked with things where you choose the data non-randomly in a way where you can get faster convergence rates on these things. So if your randomized controlled trial, you actually knew I mean, I don't know if it'll transfer this domain, but let's say I knew the people who did the observational study, and I chose the treatment of the randomized controlled trial. So that was maybe deterministic, could be randomized as well, but that can get a faster rate of convergence than a random data selection. It's usually how you draw from a really big population to get a smaller population. So I'm not sure if it would fit here, but that's another place where we've shown some faster convergence rates.
Oh, neat. Okay, well, I'll have to look into that.
Okay. Yeah.
Lynn, was that you, Lynn Bacon?
That was me.
I recognize you. You have a very like radio voice,
I do. It's from being from New York, maybe. I don't know.
I'm from New York too. Where'd you grow up?
Long Island.
Oh, I grew up in Long
Westbury.
Island. Okay, I grew up in Long Island, but it was called Brooklyn. Apparently, Brooklyn's part of Long Island.
Yeah, I was a little further east, right?
Yeah.
Yeah, people often don't identify where I'm from unless I say coffee. When I say coffee, people know, right?
Exactly.
Hey, this is really cool stuff, Dan. I wonder, could you share your random forest work that you referred to with the discrete variables? Is that written up somewhere?
Yeah, it's under revision for biometrics. But I can send you I think it's on archive, but I'll send it to you. Cool.
Yeah, and the other thing about this, this example data set is small from a neural nets perspective. I mean, most neural nets, most deep learning stuff that we do, those algorithms have a voracious appetite for data.
Yeah.
And so that would be kind of another kind of issue here. But it also strikes me that kind of what you're looking for is you're kind of looking for some theory about data generating mechanisms where you can sort of think about their behavior as your sample size increases, right?
Yes, exactly. Right.
Yeah. And so, but on the machine learning side, we sort of don't have that for the most part. Back to some of the comments that Jeff was making, it's really all pretty empirical. So there isn't, as far as I know, I mean, Jeff and others know a lot more about it than I do, but there's really no well-developed theory like there is on the statistics side.
Yeah, that's why there's a tension between statisticians and computer scientists.
Yeah.
Um,
Yeah.
Because we like, as statisticians, we like to characterize uncertainty
That's right.
in a certain way. And yeah, and so there's all that kind of tension in that regard.
Yeah,
But,
so that's
you
really
know,
part of that's the crux
yeah,
of the challenge, right?
yeah, exactly.
That we don't have distribution theory about these different components where we can examine their behavior, in the abstract, right? All we can do is, for the most part, try to run these things and do experiments. But would also actually, just a question that came to mind, and even though I'm sort of doing some work with deep learning and teaching students about it, I had never really looked to see if there are good examples of deep learning applications in experimental settings. Not experiments on deep learning algorithms, but applied in like a randomized controlled trial.
So I know, like, there's a space of literature developed by Mark Vanderland at Berkeley called the super learner. And he basically just throws every algorithm into the super learner.
Yeah.
It's called like an ensemble method, and he'll throw, deep learning algorithms in there and stuff like that. And as long as he has, so basically, this is a little philosophical. As long as the ensemble includes things that converge at the right rates, then you're okay. But I don't know. There are like ensemble or stacking methods, and so he'll throw all that stuff in there. And I'm trying to wrap my head around that theory.
Yeah, I think also the other issue in terminology here, aside from the fact that if you're from the data science side, this potential outcomes idea is really weird, right? Because, as opposed to if you're from like epi or biostatistics, you're kind of familiar with the potential outcomes and counterfactuals and so on. And this notion that the effects you're trying to estimate, you can't possibly estimate at the individual patient level because you can't observe people in more than one condition.
Yeah, exactly.
And
yeah.
so you're making some assumptions in order to make it possible to kind of estimate an average treatment effect, right?
Yep, correct.
So that's probably, but the other thing is actually the way that different people talk about convergence. So in the machine learning, deep learning arena, we're often talking about how long does it take this thing to go before we've decided we've trained it long enough, right?
Yeah.
As opposed to a theoretical consideration about if n gets large, what happens to, say, the distribution of this hopefully consistent estimator.
Yeah, how fast does it get close to the truth? Yep.
That's right. Yeah. So there's really a fundamental difference even in how the terminologies are formed.
Yeah, and I think it's important, so I know you, Jeff, you have this data science center, and I think it's, there are many people who are many definitions of data science, and it's very multidisciplinary. And I think what I look forward to hopefully getting involved in your center is really trying to, bridge the gap and kind of learn the different languages and, understand the different perspectives. And because there are different perspectives, and I think we can all help each other.
Yeah, I agree. That's why I'm open for as well.
Yeah. Good.
One kind of intersection between the two that I've thought about is if we think about some of the classification problems we do with deep learning, we can look at like the dog and cat thing on Kaggle and so on. But an interesting kind of statistical question is when I make those predictions, let's say I'm predicting probabilities for an image being a dog, how do I put a distribution on that? Right, on that prediction, right? And that's,
you mean how do you characterize the uncertainty of that prediction?
Of that specific prediction, that's right.
Mm-hmm.
Given the kind of model that we've got. Right. And there's some other things too that actually are kind of interesting. I think like mostly we're using primarily some kind of secondary data in deep learning, right? And I mean, in vast majority of cases, as I mentioned, I'm not aware of real true experimental data being used for anything. But what about, the issue of the potential impact of omitted variables?
Sure.
Because in theory, we could have the same kind of problem where we're basically approximating some functional relationship between the thing we're trying to predict, right? The dependent variable or the target, and the things we got to predict it with. And, the shape of that function that we're approximating actually may be affected by variables that are outside the data that we have available for the algorithm to learn from, right?
So how do we think? Yeah, a whole thread of my research that I really didn't talk about here is about sensitivity analysis and understanding exactly that issue. It's like, what happens if I haven't measured all the confounders, right?
Yeah.
How should I represent my inference and stuff like that? So that's a whole thread of my research that I work on.
Well, that's really cool. Yeah. I'm glad you're here.
Well, I'm glad to be here, and I'm looking for, I mean, it's really kind of, the pandemic has really, I think, slowed down the ability to make collaborations, but you know, I'm hoping that, well, if Utah ever gets its act together, we'll be able to, you know, see each other in person and be able to, you know, make it easier to form connections. So.
And even to have lunch or something, you know.
Yeah, exactly. Yeah. So I have my email address. So I'll put it on the screen again. If anyone wants to reach out and chat or want to have a socially distanced coffee, let me know.
Yeah. So someone else I thought that you might reach out to about this question is there's another new faculty who started this fall in the math department, also the Ski Institute. So his name is Bao Wang, B-A-O Wang.
Yep.
And he works on kind of the mathematics and convergence rates of things like deep learning. I think it's mostly, again, about, you know, there's some underlying proxy function that you're trying to optimize, which you think is going to give you the best generalization empirically, and how fast can you do that? But it kind of, I'm not familiar with all of his work.
Yeah,
someone locally who might know about some of these things, he might be a good person to
that's great.
reach out to.
So there is a Slack group that we created for people who are interested in statistics. Hopefully, if you're interested in that and you haven't been invited to that, please reach out to me. We had a call among people who interested in statistics at university, and so we'll have another one probably another 6 weeks from now. So if you'd like to get involved in that, please reach out to me. Again, my email's on the slide. Great.
Yeah, great. So thanks again. So and hopefully we'll continue to be in touch.
Yeah, thanks. Really appreciate everyone coming and listening. So take it easy. Have a good day.
Okay.
Thanks, Dan.
Bye-bye.
Bye.